Oftentimes, we may use datum target points to represent a fixture or assembly where a part touches on locations that represent a single point of contact. Here before us, we have a fixture that we will use to sit a part in. I have one datum target area here, one here, where our part will rest on, two cylinders here and here for datum target lines that will control the position of the edge of our part, and one datum target here that will prevent the part from sliding across our fixture. Allow me to bring in the part, and let's quickly take a look at how it sits in our fixture. I want to draw your attention to this area over here. As we can see, we have a single point of contact against our part, which is a blade, and we are aligned to that target. However, there may be times where you have a fixture where you have a circular area that is going to be touching your part, as example in this location. Allow me to bring in such a fixture. Here we can see we have a circular fixture, a fixture with a circular area that is now touching our part. However, because we have interference here, we are no longer truly representing how our part would sit in this fixture. The reason for that is because we are still being pushed to a single point of contact, but we now have an area of contact. As a result, a datum target point is not the best approach here, but rather a more accurate representation of how this part will sit in the fixture would be to use a datum target area. If I hide our part, bring the CAD of the part, and quickly hide the fixture CAD, I have the ability to create a datum target area right in the location of my original datum target point. Make sure that I have the correct properties and anchor our area. Let's make sure we extract the target. Got to make sure that we select it. Let's build the A, B, D alignment. And let's now watch our shift. We have to make sure that when we're anchoring our datum target area, that we anchor it on the CAD of the part. If I switch to our ABC alignment, we can see that we are pushed to the point on the original cone where our original fixture had. But if we switch to the alignment of the datum target area, D, we now are changing the point of contact to this location here. And we now remove the interference that we have when we are originally aligned to the point. So now we are positioned successfully how the part would sit on the fixture, and we are representing the point of contact, the highest point of contact in that datum target area. We can further exemplify this if we go and change the diameter of our datum target area to something such as 5 millimeters. We'll have a further shift of our part of how it sits in the fixture, as we can now see we change the point of contact. However, datum target areas may not be only limited to being circular. They can also be rectangular. Let's take a look at the following project here. I want to bring up a print where we have two rectangular areas noted on this print, and we are given the location of where these datum target areas are to be created. We're also given the length and width of these datum target areas. Let's take a look how we can easily create these rectangular areas in PolyWorks. Let's first focus on the small tab where A1 is to be created. I want to first show how I can easily create this datum target area, A1, by the anchor method, where I can come in and approximate the location on my CAD surface where I want to create the datum target area. Then I can control the orientation to something that matches the print by moving my mouse. We can see that we have successfully dropped the datum target area A1. However, as I mentioned, the location is given to us on our print. So if we go back to the 3D scene and I want to make sure that I am following my print, I can always access the properties after the fact of my datum target label and change the location to match the print. So if we change our location to 2015 and simply hit apply, you will see a change in position in our datum target area. And since we saw no movement, we most likely anchored in the correct location. Let's go ahead on to datum target area A2. If I come in here, I don't want to have to anchor and go back and readjust the position. So allow me to draw your attention to the numerical method. Here, I can directly apply the proper location for where that datum target area is supposed to be. Keep in mind that I am controlling the location of the center of the area. And let's go ahead and make sure we apply the datum target label, A2, and hit create. Now that we see datum target area A2, let's move to the front of the part where we have our last target, which is datum target area A3. This is a circular area, and we should now be comfortable with creating these circular datum target areas. So on the first part, I anchored my datum target area on a CAD surface. But if we take a look back at our print quickly, we can see that the circular area is over the hole. As a result, I can't anchor on a CAD surface, but PolyWorks does allow me to anchor at the center of my circle and allowing me to have that datum target area created. If you forget to apply the datum target label, once again, you can access those properties and apply the label after the fact. Let's go ahead and align to these newly created datum target areas. And go ahead and run the datum reference frame. And here we are. So we are now aligned to those datum target areas. If we go back and look at the print, we have 3 position callouts that I want to go ahead and build into our inspection. Let's first look at the back hole. We have a position callout to datums A, B, C, so we can quickly create that on the back hole. If we go back to the print, I want to talk in detail about the position to only datum A and the position on the front hole to only datum A. While this first position is controlling all degrees of freedom, the second position callouts are not. So let me first create those and then discuss what's going on here. So I'll apply the datum feature of A. And I want to discuss what we're asking PolyWorks to do. For this position control, these 2 to only datum A, we are only locking translation along Z. As a result, we can still translate in X and Y directions and rotate about Z. This gives us the ability to optimize the residual mobility of the position on both the front hole and the back hole. In PolyWorks, residual mobility is used when we're not locking all degrees of freedom. This means that the part or a feature is free to translate and or rotate in certain directions. Well, PolyWorks now allows us to calculate this residual mobility on these datum target areas. However, residual mobility can take a few minutes to calculate. So for today's webinar, I don't want to keep everybody too long. So I'm going to go ahead and pop a project. We've already gone ahead and calculated those values. So it probably just needs a couple more seconds to calculate. But we can see the deviation here is successfully calculated at 0.21 and calculated here at 0.21. Looking at the deviation of these 2 holes and seeing that these if the deviations are evenly distributed between them, we can see we have successfully calculated the residual mobility. Last but not least, today, I want to quickly open up a blank PolyWorks Inspector project, and I want to show how if you have a native CAD with the datum target areas entered by your design department, you can bring those datum target areas in with your native CAD very easily and already have the datum target areas there waiting for you. So if I go ahead and bring in this part, we can see our datum target areas are successfully present on our CAD surfaces, as well as some points in the back. That concludes today's webinar on datum target areas.
Thank you, Joshua. So yes, we have a couple of questions here. When creating the rectangular area numerically, in this case, it was easy since the desired orientation was square with the standard axis. But how would you recommend proceeding if the area needs to be oriented based on the edges of the part?
That is a great question. So if I understand correctly, if we take a look at this part here, we have our coordinate system that's square to the corners of our part. Imagine if I had to create a datum target area here that's parallel to perhaps this line if I want, which is not square to our coordinate system. Well, I could use some objects such as a vector to control the orientation by simply anchoring a vector very close to that line there. And then if I want to control the location, maybe it's told to me on the print, the location, the XYZ, or maybe I need to identify a location. But in this situation here, I could just anchor a simple point to control the location of the center. Then I can go create that datum target area numerically as a rectangular area. And for this situation, we can apply it to datum target label E if we want. And then I can use the drag and drop method you may be familiar with and just simply drag in the vector orientation as well as the point location of our datum target area. And we can see we successfully create that datum target area that is parallel to that vector.
Thank you, Joshua. And another question. You mentioned datum target points and lines. How do you create those?
That is another good question. Just to quickly go back to this part, as I mentioned earlier in the webinar, we had our datum target points and our two datum target lines. Those datum target points can be found here, and to create those datum target lines can be found here. And if you want more information on the different properties, the purpose for these, and how to create them, I'd like to direct you to a previous webinar that we made that specifically focuses on datum target points and lines. You simply go to our YouTube channel and just search for datum targets. You can take a look at this webinar here that will go into some great detail about datum target points and datum lines.